Battery Generation, brought to you by Celeste.
Welcome to Battery Generation, your podcast on electromobility and European battery research. Leonard, good to see you again.
Likewise, Patrick.
Leonard, I'm absolutely pumped for this show. As you know, the industry works pretty hard to get our European green battery production going, and one of the most discussed topics in research is battery recycling and the circular economy of battery materials. Keep in mind, without this approach, we'll probably never get to net zero emission batteries.
Absolutely. And dear listeners, before we start, if you want to listen to us more often, hit that subscribe button. And if you have an idea, a topic, or you have someone in mind that we should discuss in our show, send us an email at hello@batterygeneration.com. That's hello@batterygeneration.com. And if you want to do us a solid, give us a good rating in your favorite podcast app, be that Spotify, Apple, Google, or whatever the podcast app of your choice is. Thank you so much.
Normally, we're talking to either scientists or industry representatives. This time, we're talking to both. An industry innovator and scientist at the same time. Welcome to Battery Generation, Professor Emma Nehrenheim from Stockholm, Sweden.
Hello, thank you for having me.
Emma, let me introduce you to our audience. You are Chief Environmental Officer at Northvolt and a professor in environmental engineering of Mälardalen University. So you're a scientist and an industry innovator, now on a mission to deliver the world's greenest battery within your job at Northvolt. So Emma, Europe's largest battery recycling plant is now being built at of Northvolt, your first gigafactory in Skellefteå, Sweden. How are things evolving over there?
It's going quite good right now. We are just finishing up the building and the internal steel, and mid next year we are expecting that plant to be up and running. It's pretty fascinating. It's about 4 gigawatt hours of recycling capacity that we are looking at up in Skellefteå.
Do you know how many batteries are already being recycled in Sweden or maybe even in Europe?
It depends on what you mean with recycling. You know, recycling comes with a lot of process steps, and it involves collection and pre-recycling. And if I make a good guess per year, I think it's somewhere 30 to 40,000 tons at this point in time in capacity that we have. And that's not capacity all the way back to a fully circular. So that's just managing volumes in any shape or form. It could be just disarming. It could be, you know, a very early pre-processing step. But so far, as of what I've seen, there is very, very little capacity to get the batteries back as metals of battery grade.
We recently produced an explanation video about this. There was the number of 55,000 ton a year in Germany, for example. And I always ask myself, is that actually a lot when you compare that to other continents, for example, to US or China? And how are we evolving? Are we on a great path towards sustainability, or is that comparably low?
Recycling for me is the absolute key to making this industry what the industry should be. But we also have to remember that we are building this industry right now. I mean, most of the automotive companies are sort of in the cradle. And you could say that, yes, we are a little bit too late, but the time is actually perfect right now, I think.
You just mentioned critical materials that you want to win back out of a battery. What minerals and metals are they?
For us, these are the metals where we need to tap off a market that's not really there, that needs to be built up, and where we see that this market will be squeezed in the coming years. It's the lithium. I mean, there is a lot of lithium on the planet. It's mined in very different ways. We have between brine and ore-based lithium, we have different sustainability issues. We have seen that there is the resources are there, but the refining capacity is really not. With the sustainability targets we have, we're setting up refining for it in Portugal just to solve this. So that's one really critical element. Another one is cobalt. where it's an important stabilization a component for the cathode material. And the cobalt is also something where we need to expand in short time quite a lot. And it's a global mineral that has been difficult and very resource demanding for us when it comes to auditing processes, for instance, for sustainability. So a very critical material for us. The big one going forward is going to be nickel. Nickel has been a big metal globally so far, but the nickel content in the battery is increasing with higher performing batteries, and the nickel market is getting more and more squeezed. We saw that coming already years ago, that nickel is going to be a key component, and this is really going to be one of the big sort of talking topics for the battery industry with nickel. So that's also one of those that we're going to have to keep an eye on, and where we have a strategy to recycle as much as we possibly can.
We already have a great, in my eyes, system, a refund system for lead acid batteries, for these batteries that are also in your traditional combustion engines that you return with lithium-ion batteries. That system does not really apply to many handheld systems, but is there already a system for electric vehicles and their lithium-ion batteries? For example, when Volvo now produces a car with Northvolt's batteries, are you forced at Northvolt to take back these done batteries?
A lot of questions in one. Let's start sorting it out. So for one, when it comes to lead acid, I agree with you. I think that system has been worked out very well so far. It is quite a lot easier for lead acid, since you yourself can change your battery in the car and actually hand it in to a waste station somewhere in Europe, and it will be managed and collected. However, you also always bring your car to service. So if you go to the service workshop and you do the service on your battery or do a checkup on your car, you can have that system built in there if you want to change the lithium-ion battery, and that can actually be solved over time. What needs to happen in order for that to sort of be in your daily life is the scale of economics. So right now, the number of EVs are so small that it hasn't really been coming into place in the same way as we see with the lead-acid batteries. When it comes to the specific question on Volvo, yes, there are many ways for different models. We will definitely be able to close that loop, and the ambition is to take all the batteries back and make a new battery of each and every one of them. And it's a little bit different on the definition of batteries. But yes, we are of course obliged on our market to take back the batteries and do recycling.
So, Professor Nehrenheim, I understand why recycling is so important to Northvolt. Could I ask you, how are you organized, your recycling branch within Northvolt? I've read something about Hydrovolt and Revolt. How are these programs and plans kind of organized within your company's structure?
So Revolt first, that started as the recycling initiative within Northvolt. Already 5 years back, we decided that recycling was such a strategic thing for Northvolt, for the sustainability mission, but also again for the raw materials strategy for the company. And Revolt is a fully owned entity. It's its own entity within the company. And the aim is to produce the battery grade materials that we need for the cathode material production. And that entity will always do a hydrometallurgical process and very close to the cathode material production. And then when it comes to the sourcing to that feed, we have a very close relationship with the customers, and we bring the batteries back to us. But we also want to offer something more than only recycling for our own batteries. So on top of that one-to-one relationship we have with the OEMs that we or the car makers that we are working closely with, we have, for instance, Hydrovolt. And Hydrovolt is a joint venture between us and Norsk Hydro, Norwegian Hydro, which is a company that is specialized in aluminum. So since we want the cathode material metals, and the Norwegian company wants, Norsk Hydro wants the aluminum, it's a perfect match for having a joint venture for recycling. Also, the Norwegian market, as you know, is a pretty early market when it comes to EV evolution, and they've been building their car fleet of EVs for 15 years or so. So there is already a recycling feed on that market.
How many electric vehicle batteries are already flowing into these recycling plants? What are the first numbers, and how many batteries are you expecting in maybe 5 to 10, 15 years?
The volumes will probably grow exponentially. The curve is, of course, a few years behind the curve on the EV buildup on the market, but it's getting there. And this year, I think in Norway, we have almost filled that plant of 8,000 tons. So there is a buildup of volumes coming into the Norwegian plant.
Good luck, first of all, for these very exciting plans. We're now talking about the different processes. You just mentioned something about these terms already. They're called pyrometallurgic and hydrometallurgic recycling technologies. Could you, first of all, give us a broad difference between these two very, very different approaches?
So depending on where you start in the process, you have to do some kind of pre-recycling. So you have to bring the materials into site and do the first dismantling and the disarming of the batteries. And then after that, you need to refine the metals to bring them out one by one. The pyrological process has been pretty common. There are many different ways of doing that. Pyro specifically is more oxygen-free. There are different temperatures that you can work with and different sorts. The challenge that we find with pyro is that it's more difficult to grab the lighter metals, such as lithium. They tend to build something called fouling on the surface of the oven that you're incinerating in, and it can be the losses can be higher. But I know that some are also successful with this, so who knows? This could be also going into a brighter future going forward. We had a situation where lithium was very important. Lithium, as you know, has a very high footprint when you mine it, especially with the brine source of lithium, where you have the salt desert that are tricky for us to handle from a sustainability perspective. So therefore, we want to catch any lithium that can be caught in the recycling process. So we want to keep the process cold. And that puts a little bit of more pressure on us in terms of disarming more gently in the beginning, and also cold crushing of the batteries to keep as much of the lithium in the process. On the other hand, when you do thermal, the good thing is that you get rid of some of the carbon-based components, such as the electrolyte, for instance. So there are also advantages of using a high temperature process, of course.
When you say get rid of them, you mean you burn them, right? You burn the graphite. So you're not getting graphite back, but you're burning it.
Exactly, and also the electrolyte.
So this whole process, how long would you say does that take in general? You mentioned already what minerals can be won back. So you said lithium you can win back, but sometimes not as efficiently. So which ones can you get back, in fact, and how long does this whole thing take?
So we are only in the beginning of this. We can separate everything. In our process, we can separate out a very clean graphite, for instance. And we have several projects working forward towards a recycled graphite system. But we are not yet there yet. It's a pretty difficult thing to do. On the other hand, most of the other components we are separating one by one. So we get aluminum, we get plastics, we get copper, we get all the NMC, the lithium, separated from one another in the process.
That's you're talking hydrologic.
In our process, it's under one roof. So we do first we do crushing, we crush the material, and then we do a sorting stage. And then after that, we send it directly into the hydromet. And then we dissolve it in acid and separate them one by one. And if the metals are not clean enough, they're sent back into the loop so that we increase the yield all the time.
In general, could you list once more all the metals and minerals that you can actually win back with that process, which are lost with the pyrometallurgic process?
Even after a pyro, you should and you can use a hydromet. Yeah, so even after that, to get it to battery grade, you can use a sort of wet chemical or a hydromet process to refine and get the metal sulfates that you need for the final product sent into the battery grade. In the hydromet, what you basically do is that you remove the impurities and or you remove the metals that you want in a stepwise approach and take them one by one. So it's a really delicate process where you separate them either with pressure, temperature, or a solvent extraction process. A little bit different design for different plants, depending on what impurities you have and so on. A hydromet is not a new thing as such. The hydrometallurgical processes have been used widely in the mining industry for basically the same thing. If you take any of the hydromet processes that produces for the metal industry today, it's almost exactly the same, but they use ore instead of recycled batteries when they separate the cobalt and the nickel. What we get out in our hydromet is the nickel, cobalt, manganese as sulfates. We also get copper as sulfate, and we get a lithium hydroxide. Which is also something that is very valuable for us and good for the sustainability of the Northvolt battery.
So just to get a clear understanding, those materials you get out of the hydromet are not directly, you can't directly make a new battery out of them, right? You have to process them once more to get the clean element. Is that correct? Did I get that right?
Quite the other way around, actually. So,
okay.
Yeah, good that you ask. So most cathode producers that do NMC 811, which is the cell chemistry that we currently have, and need NMC sulfates and lithium hydroxide. We can also use metal as briquettes or in their elementary form, but then we have to first send them through a process on site that we call dissolution, which is where the metal become metal sulfate. So it's a pre-step. But the recycling gives us exactly the metals we need. The things that are incredibly important from a battery manufacturing perspective is that they need to be super pure. There can be no trace elements following the metal, such as there can be no iron, no aluminum, no lead. So it's tricky when batteries are blended with other batteries. Normally, EV batteries are not blended with others, but you can have NMC batteries coming in other feeds, such as e-bikes, for instance. Then there can be a mixed feed of different cell chemistries, and that becomes tricky from a recycling perspective and from a battery grade. But otherwise, we actually get the perfect chemistry.
Hydrometallurgic sounds very healthy, but now that I know that a lot of acid is actually used in a pool there, how sustainable can this process be?
I mean, I think it's very sustainable. So first and foremost, you have to remember that in any metal refining, you need a purification step. And the best way to purify is to bring it to its elementary form, meaning dissolving in acid. But The acid can be recycled. That's number one. And also, the acid is just one component, and it's a byproduct for most other industries. On the other hand, what we have done is to remove a lot of steps that comes with organic solvents. So we are using a lot of pressure and temperature to separate the metals from each other. And we are trying to reduce significantly the number of organic solvents needed.
You're already mentioning some points for optimization there. You're working with pressure, with temperature. I had a thought on your comment before. If you actually can use the materials coming out of recycling directly for the creation of new batteries, that might actually be a competitive price advantage, right? I mean, from the mining, they have to do one step more and then they can sell it. I don't know. Is that is that something that could scale up economically in time, especially when, of course, mining gets more expensive?
We definitely think so. I think that when we reach the economics of scale of recycling, and at the same time when we learn more about how to optimize the flows, because one thing is expensive, and that's the hydrometallurgical process, so the wet chemistry. Another thing that's expensive is the collection and the flow back. And when we optimize that altogether, definitely. I mean, fundamentally, crushing a mountain and dissolving that in acid should not be more cost effective than taking one battery that contains exactly what the other battery needs and just cleaning that up and sending it into production. So you're absolutely right. I mean, the numbers are there. It's just a matter of walking the talk here.
Which statement would you say best describes Northvolt's battery recycling efforts? Is that a further development of batteries, including critical elements, and establish a well-working recycling process, as you just mentioned? Or maybe B, develop innovative battery cells where battery recycling wouldn't be as important since materials are more abundant, cheaper, and sustainable from the beginning. So which path do you think rather describes your efforts?
Difficult to choose between the two. The core message that I want to give is that at 2040, when the market is fully mature and we have a one-to-one relationship with the batteries going out on the market and the batteries going in, you will have, for LFP and NMC, a almost one-to-one relationship. And then it's maybe 90% of the metals in the first battery that goes into the next, and you will have a very small feedback in. So my expectation is that the refinery of the metals comes from batteries. So a fully closed loop for the chemistries, but they need to be on separate paths. And you can recycle LFP. It's super easy. But there is one problem, and that is the LF, because F is iron. And iron is a killer in a nickel-based chemistry. It creates shortcuts and thermal runways in the chemistry. So you never want to blend those two. It's much easier to recycle LFP and produce LFP chemistry, but it cannot be in the blend with the NMC.
Basically, your recycling plant, and so everyone seems to kind of tune in on the whole NMC set as of right now, it seems, yeah.
Yeah, I mean, if you want to replace a 5 Series BMW that's going to go between, I don't know, Munich and Frankfurt, LFP is like asking them to drive a Nissan Micra. It's not going to fly. But there are lots of people who need a Nissan Micra, but it's not the same people.
Plus, the business model is something totally else, since there are no metals that you necessarily have to get out of these batteries, since they're very cheap, and maybe legislation has to force you to recycle them, right?
I agree to some extent. On the other hand, it's also pretty cheap to recycle them, so it should make sense.
That's amazing news. Because I think a lot of us have in their minds that recycling is something very expensive and that this will only work if the mining and the new materials are very, very expensive to get. Otherwise, no one will do it, because we live in a world where we basically just throw everything in the trash. We are very, very far from circular, and now we're trying to electrify everything. We're trying to do this transformation, and then I think this is a very valuable information you're giving here, that this is actually sustainable and it works economically.
Absolutely. It has to work economically because we're going to have to make it. I mean, we can't continue tap off the nature forever. I mean, we need to build this, and we need to find the scale of economics, and we need to optimize these processes so that it's working well. And you have to remember that this is really the first time it's moving into Europe. And in Europe, we are extraordinary good at industrial optimization. So we've only seen the beginning of this.
You mentioned before that you have different steps in the whole recycling, and we've heard that that you can disassemble a battery with the help of a robot, but then you need to work very closely with production. Is that something you have in mind, something you're focusing on, or do you prefer to use the agnostic crusher that will just shred it and say, I don't care about the form?
It's a little bit of both. So we need to take the modules apart from each other. And it's also about making the most bang for the bucks. So if you look at the pack, what you have in a pack is a great source of aluminum. So the pack itself has a very fine aluminum shell. And that should definitely not be sent into the crusher and contaminated. So first you want to remove the shell that holds the modules and the battery management system, the BMS. When you take out that, you can just as well separate the BMS from the modules. So that I think should be done in a at least automated way. And then again, you have to sort of calculate where the break even is between how much you optimize that process and how much can be sort of man-made. We have, for instance, decided that for any hybrid system, we do not focus on automation at all because it doesn't make sense. We think that the hybrid cars will sort of be smaller in volume. The hockey stick is not really there, and it's pretty easy for a person to lift those modules out. It's not ergonomically a problem, for instance. But when it comes to the EV packs, it makes sense to industrialize. And we are focused on crushing on module level. So we take the pack apart and we crush the modules.
Are there any caveats? So do I have to make trade-offs if I optimize maybe a production that the cell will be easier to recycle? Do I have to make trade-offs when it comes to the performance of those batteries? And how are you handling that at Northvolt?
It's a really good question. And I can only answer from the experience of the batteries that we have so far. And what we've seen so far is actually that it's a little bit the other way around. Because honestly, if you take a good engineered battery from a company that is rock stars in manufacturing, you can clearly see that the smartness in how that battery has been manufactured can also be used in the reversed manufacturing, meaning the recycling. So you can see how it's pretty easy to set up a dismantling line from one of those batteries. And then you can also see that the performance of those batteries is really good. And then how this will look going forward is going to be super interesting because now we are discussing so many things around how to put the screws and so forth. But I can take one example. So some batteries you can have as a screw that where you take off the lid, where all the screws are in the same direction and the same dimension. Then it's super easy to dismantle, but it has also been super easy to manufacture, right? So it goes a bit hand in hand.
Let's say you build this perfect process of recycling and you win back these, let's say, 5 materials, right? graphite, lithium, nickel, cobalt, and what did I forget? Manganese, maybe copper. Which one of these materials can you use straight away as clean and fresh as they would come from a mine directly for the new batteries? Is there any sort of quality difference after the recycling process?
Right now, for nickel, manganese, cobalt, lithium, super quality. We can take it straight back. For most of the aluminum, the same. And as I mentioned before, it's quite a lot of aluminum. You have aluminum in the casing of the cell and in the pack casing. So aluminum is incredibly important. And as you mentioned with lead acid batteries and the lead recycling, aluminum already have a perfect recycling supply chain. Graphite needs some more research before you can get it pure enough and before you can get the particles in the structure that you need. Since it's carbon-based, it has a certain structure that we need to get back.
Professor Nehrenheim, let's now talk about the European regulation about battery materials. There has been a European framework legislation even for that. Could you briefly explain what happened there in Strasbourg and Brussels, that battery legislation now affects your business model even? What's inside these laws?
It's a lot of things, actually. I think that the regulators, the European Commission and DG Environment has been pretty bold here. They've been fast and they have clearly understood where this market is going. They have put together a regulation that puts a backstop, one might say, to the market. It includes targets for recycled content. What we are used to is a responsibility for end-of-life products, that you need to have a system where you take care of it. Instead, the regulators this time said you need to make use of the metals available for recycling, and you need to prove that your products have actually utilized those resources, which I think is an amazing way of looking at it if you really want to close the loop. So that's number one. They've also proposed a carbon footprint target, which I also think is bold and also a sort of a stop or a blocker for the worst performing batteries, which is also something that I think is very encouraging. And it's going to be really interesting to see how all this ties together. But only the fact that you're now supposed to declare your carbon footprint and then the amount of recycled content that you have in your battery cells is really something that is never heard of, I think.
And does this battery passport change anything for Northvolt directly, or are you already all set and you just continue?
I mean, I would be the happiest person on earth if Northvolt was all set with everything. It will not change too much. I think that it's good to have this regulatory framework pushing us the last mile on this marathon. If we would have these requirements and not having a way of declaring, it would be there would be no point of having it. So we welcome the battery passport. I think that the battery passport will be great for traceability. The devil is in the details now. So it's going to be interesting to see if we have a full declaration. I mean, what batteries enter into our market. The demand is enormous, and to see what actually will be declared from all the battery makers on this planet. But for us, it's not a game changer, but it's really good that we have it already now and that it's described.
Could you explain this a little more in detail? So when I buy, as an automaker, I buy a battery from Northvolt, and does it say, for example, half of the battery material comes from a former done battery from China, and half of it is bought from Northvolt directly? I mean, you have to declare what's inside the battery from the point on when this European legislation comes into power, right?
Yes, but as I have understood it, and I don't know the exact details on that, you will not get many lives back. So it will not be a sort of on each and every element that you have in the battery. What you're going to have to state is that the recycled content in the battery and the carbon footprint. And that's going to come with, and I don't know if you know how you buy refrigerators, for instance, but as I've understood it, it's more like a certificate. So that's it. On the other hand, I think that itself, for most battery manufacturers today, is going to be pretty challenging. That's, I think, is the level of information that you get. And then, going forward, we will see what will happen. I think that there will be a voluntary journey for some of us.
Thank you very much for these insights and your time, Professor Emma Nehrenheim. Dear listeners, now it's your turn. If you got any questions, please email us. That is hello@batterygeneration.com. You may also comment in the comment section below. And as always, make sure to subscribe if you listen to us for the first time. For more, click in, tune in, and stay charged. Bye-bye.